knowledge not of fact but of values. It is on occasions like this we get opportunities to test our knowledge and understanding. Let's start this event with a silent prayer. Thank you. I would like to welcome Dr. Vijay M., Assistant Professor at Department of Mathematics, St. Thomas College, and also the convener of this workshop to introduce the resource person for the session.
Good evening, all. It's the second day of our instructional workshop on advanced cryptography, IWAC 2023. And we have Mr. Murthy DHR from Presidency University to deliver his lecture here. And there will be a hands-on session also. Mr. Murthy DHR is working as the Assistant Professor in the Department of Computer Science and Engineering at Presidency University, Bangalore. He is currently pursuing his PhD at Presidency University after completing his MTech from the University BDT College of Engineering, Karnataka. He has worked on the 12th five-year plan project of CSIR in HPC and Cybersecurity Division at CSIR 4th Paradigm Institute, Bangalore. Mr. Murthy is also a life member of the Cryptography Research Society of India. He had previously served as Senior Executive in Academic Training, Sadhguru Tejas Center for Telecom Technology. Hearty welcome Dr. Murthy DHR to the Department of Mathematics on behalf of the entire faculty and students of our mathematics. Welcome, sir.
Thank you very much. Thank you very much, Suji ma'am. Am I audible clearly?
Yes, sir, you are audible.
Okay, fine. Thank you. Good evening, one and all. Thanks to the management to give an opportunity for me to share my research experience in the field of RSA public key crypto. So before beginning my PPT, my presentation, so I don't have too much of a slides or a theoretical oriented content here. So my agenda will be like motivate the audience or motivate all the researchers to take part in the RSA public key crypto system. What is the real challenge? Where and all you can apply RSA algorithm? What is the complexity behind that? And I will be taking you to the Sage Mathematic Library. I'll show you the demonstration, and probably who are having laptop, you can also work parallelly with me. So, and all finally, what are the research avenues? Like as a MTech, as a MCA student, MSc Math student, how you can take up this career, and preferably, if time permits, I'll be giving you one or two labs who are working on this RSA core research. I mean, as you are all mathematics background, so we need people. So, unfortunately, what is happening here is I'm from computer science background where I know how to code, but the pure mathematics, like mathematics people, you are little away from like how to write a software or how to incorporate cryptographic algorithm into networking, into a protocol. So definitely, if we both join together, that is mathematics and computer science together, definitely we can do wonders. This is what a small introduction. So uh, I'll just share my screen. Is my PPT visible? Can anyone confirm, please?
Yes, sir, it is.
Okay, thank you. I assume that maximum audience are from mathematics background. Hopefully, I'm right.
Yes.
Yeah. Okay, fine. So, in your masters, in your bachelor's degrees, you might be aware of prime numbers. You might be aware of GCD, or you might be very enthusiastic, like fast, very quick mathematical calculations on prime numbers. So, uh, but during my school days or during your school days, you never thought that your prime number will rule the world. Your prime number will be a part of your day to day life, right? So, what I'll do now, I'll just start the slideshow. Yeah. So the title I have given is Key Insights of RSA Public Key Crypto System. So to start with, my flow of the PPT will be like this. First, I'll give an introduction. Probably many of you are aware of the introduction to public key cryptography. So, but just 4 to 5 minutes. Then, what is introduction to RSA? And who has invented all those things? The strength of RSA, the main pillar of today's discussion. Then, how to deal with a large prime number. As I told you, I'll be demonstrating a Sage mathematic library. Then implementation guide, especially needed for mathematics guides. Then research avenues in RSA, whether still we have to run behind prime numbers or there is one more alternative available. Let us see. Recent trends, what happened in the field of RSA, and followed by some references. So hopefully you are familiar with this diagram. Definitely, I think yesterday also one of our speaker was talking about this public key cryptography. So the problem is like you should understand the very basics. Now, in all the cryptographic algorithms, we need to talk about key. Like, what is this key? Basically, it's an integer, it's a character, is it an hexadecimal value, or a combination of a special character with a number, whatsoever. Basically, we are using that to convert your normal plain text into ciphertext. A simple example, I'll just write one message, St. Thomas College, Thrissur, that anybody can read and understand, right? But when you put it into a cryptographic algorithm in your communication, this message will be moving over a communication channel as a ciphertext, which no one can understand. That is what we call it as a ciphertext. So we need a key. Yes, definitely we need a key. For what purpose? Converting plain text into ciphertext and ciphertext back to plain text. So by using this key, we have two broad categories of cryptography. Number one, symmetric. Number two, asymmetric. Asymmetric is nothing but public key cryptography. Symmetric, the best example is AES and DES. Unfortunately, your DES is no more. We cannot use data encryption algorithm. Yesterday, I think you might have get in touch with DES algorithm. So it is no more. Triple DES also no more. Yes, we can go ahead with the AES, Advanced Encryption Standard, in the category of symmetric or private key cryptography. Today, what I am talking about, it is asymmetric or public key. You might observe, see here, I think I'm just pointing the cursor. So if I want to send a message to Vijay ma'am, where in public key cryptography, each and every individual in the communication will have two different keys. Number one, public key. Number two, private key. The public key of an individual can be shared with others. For example, around the 30 to 40 members are there in the team now. My public key I can share with anyone. Absolutely, there is no problem. But the private key of an individual is confidential. Hope you understood. The problem is now I want to send a message to Vijay ma'am. What I'll do, as the basic concept of public key cryptography, I know the public key of Vijay ma'am and Vijay ma'am know the public key of mine, and same thing applicable to all the members in the team. So what I will do, I will pick the public key of ma'am, I will encrypt the message, I will send. What I will send? Ciphertext I will send. So once madam received the ciphertext, madam has to get back the original message. What is the meaning of it? For that, madam use the private key of, madam's private key, which is known to only one and only recipient. So this is the basic agenda. Suppose the message which I sent to Vijay ma'am is trapped by some other mysterious students in the group, but he or she could not get back the original message at any cost. Now the point here is, in this RSA algorithm, how do you generate public key? How do you generate private key? What is the logic behind that? Why this algorithm is so popular? Right? All these things we have to go upon. Uh, any audience at any point of time, if you are feeling any doubt or anything you want to ask, no issues, no problem. You can interrupt at any point of time. No issues. Even if it is simple thing or complex thing, I'll try to answer to the best of my knowledge. So what about this RSA algorithm? If you look into the year when it is established, 1970s or in between, I mean before 80s only. Just can you imagine the computational resource at that time? We had supercomputer? No. We had any i5, i7, i9, i11, 4th generation, 10th generation? No, nothing like that. Where these three cryptographers, Rivest, Shamir, Adilman, these three people are the founders of RSA algorithm. Okay. So now the key, just now I talk about key. This key is, I mean, these two keys, sorry, I mean, two keys, public key and private key, are generated. When public key we are generating, private key anyway, you need not to have any high level mathematics because it's a confidential thing. No, my public key you can know, but my private key nobody know, just like your ATM pin. So based on the prime number, we are going to generate. So why this algorithm is so popular? You can see the last sentence on the slide, because of the factorization problem. Okay, factorization problem. I think you are all mathematics guys. You know that it is very difficult to get two prime factors from a large composite number. This is the beauty of RSA. So, and also it is very difficult as you just increase the number of the length of the input, your factorization will be exponential. It will be exponential algorithm. So, a suggestion to all of you, when you are developing any cryptographic algorithm, your what is that? Your as a developer perspective, it should be linear. As a hacker perspective, it should be exponential. That means it should be very, very difficult for you to, for a hacker to get the decryption. So in 1983, so these three cryptographers, they got patent from MIT, Massachusetts Institute of Technology, USA. So now, how to choose the prime number, and we have three more variables which will be included, which will be calculated based on the two prime numbers which you have taken. Then your algorithm works like this: key generation, you know what is key distribution, that is the exchange of key between, or just now I told you I can share my public key to anyone, key distribution, then encryption and decryption. So look into these equations. So select P and Q, and most of the textbooks, this screenshot I have taken from William Stallings. Preferably I'll give that reference later. William Stallings, its most popular book. Where suppose being a mathematician, if you want to get into cryptography, I advise you to use that book as a beginner. So P and Q are the prime numbers. I'll put a note here: for better result, you have to choose P and Q which are resides apart. For example, a value of P in terms of hundreds, value of Q in terms of thousands. So that's the best advice, so that your the complexity of your algorithm will be better. So how and all we will see later. For better security, you cannot take a two prime numbers like 3 and 5. I mean to say, don't take prime numbers which are very near to each other. Don't take 11 and 13. Don't take 13 and 17. If you take 3 and 17, okay, little bit okay. But if you take one prime number in the terms of tens or hundreds, the another prime number will be very far. Then that will increase your performance. So next, what we'll do is we will multiply these two. Yes, we will multiply these two. Then next third point is this. I think you are seeing one symbol phi of n. You can just put a note. This is also called as Euler-Totschen function. I'll be showing you how to find the Euler-Totschen function for a given number. Any number. I will show you whatever the length of the number you tell. I will show you the demonstration. After this, select an integer e. What is the rule here? GCD of Euler-Totschen function, which you have just calculated, with the number what you are going to choose, they are relatively prime. Relatively prime. So you know which is the best method to calculate the GCD. So I can say Euclidean algorithm. Yes, we can go for it. So E, just wherever you see the letter E, it is encryption key. Now calculate the D, which is inverse modulo phi of n. So for this purpose, I use extended Euclidean algorithm. Probably as a mathematician, you come up with a new, better algorithm. Yes, of course, I'm not telling it's not possible. So what is how quick you can calculate the GCD? Yes, how quick you can calculate your decryption key. So E means encryption key, D means decryption key. If you can remember the diagram which I have shown in the second or third slide, in that there was public key and the private key. So for encryption, which key we are using? That is E. Is it public or private? The value of E is public or private? Anyone?
Public.
Good, very good. So of recipient, of the receiver side. So D is decryption side, which is known to one and only that particular receiver. Understood? I mean, a simple explanation about RSA. So encryption. So here plain text. So I'll put a note here. As a mathematician, you will feel difficulty, like I have a message, how I'll convert into number. So I can write 10 to the power of 22 mod 69. Fine, no issues. But if I give a character, then how to convert that into an integer? The best way, I'll tell you, you can take the ASCII code of that particular character. Say, I want to encrypt R, or a small letter R or capital letter R. So probably you are aware of, if not, please make a note. That is, if a character is given to you, the best way to implement the encryption or decryption is by taking the ASCII code. ASCII code is nothing but integer for that particular character. Whatever the key is available on the keyboard, whether it is a special character 1 to 10, including the 0 to 9, small a to capital, small a to small z, capital A to capital Z. So we have a particular ASCII code, ASCII, ASCII code. So if it is a character, I cannot write a to the power of 10 mod 25. What I can write? I can write a number to the power of another number. So here in this slide, what you are seeing, the message M. So this is, if it is a character, you take the ASCII code of that is ASCII code is nothing but an integer. Understood? Now the decryption. See here, you can observe one hint. M power E. E means encryption key. Look into the decryption equation. C power D. See the exponents. It is D. So E and D, wherever the exponent E I am using for encryption, wherever the exponent D I'll use for decryption. So let us take a quick example, a simple example. Quickly, we can have a look at. So two prime numbers are 7 and 17, right? Now, what is n? Just multiply these two, no problem. Then this is Euler-Torsion function, step number 3. We have a formula. Please make a note. Euler-Torsion function for a prime number is p minus 1. Suppose, see here, 7 is prime? Yes. Euler-Torsion function of 7 is 6. 17 is prime? Yes. Euler-Torsion function of 17 is equal to 16. Even you need not to worry about whether it is p minus 1, whatever it is, just directly minus 1, multiply these two and you can quickly get the answer. What happens if the given number is not a prime number? Like Euler-Torsion function of 8. In that case, you have to find the GCD from 1 to 7. In each iteration, how many times it is relatively prime, that count is going to be the GCD. I'll just show you in the demonstration. Now, see here, I have just shown you the condition for E. That is, what is this E? Encryption key. So how to calculate that? By using GCD. Now please look into this. Now phi of n is 96. GCD of 5 and 96. So they are relatively prime. Yes, I can go with E is equal to 5. You can ask me a question. There are so many possibilities up to 95. Which one to choose? Yes, it's up to you. It's an agreement or it's a mutual key agreement. There are some protocols are there. So whatever the possibility of E, there is no rule that you have to choose the first value or last value or the mid value. Now GCD of next I'll go with 6. GCD of 6 and 96. They are relatively prime? No, definitely no. Both are even number. 7 and 96, 8 and 96, 9 and 96, 10 and 96, 11 and 96. I think probably the next one more value can be 11. So just I have got relatively prime for E is equal to 5. No issues. Now E is equal to 5. What is this? Encryption key. How you got this? Based on these two prime numbers 7 and 17. Next, D. What is D? Decryption key. How to find out this? This is possible using inverse modulo operation. Inverse modulo operation. That is extended Euclidean algorithm. We can easily find out using one line statement. I think not a big deal. Okay, so you can just look back. E is congruent to E inverse mod phi of n. I think in my example, E is equal to 5. E is equal to 5. Right. So 5 inverse mod, what is the value of phi of n? 96. 5 inverse mod 96 is equal to 77. So that is how your decryption key is calculated. So next, let us go back to step number 7 and 8. A simple analogy, E for encryption, D for decryption. And what is the public parameter? N, we call it as a public parameter. You may ask me a question. Sir, you told the public key is known to all others. Fine. A hacker perspective, I will talk. Hacker. Suppose I am sending an WhatsApp message to you. Assume that somebody else trapped my message. The only possible way to get back my key is prime factorization, which we are going to discuss in the upcoming slide. So now, so an example, plain text is equal to 6. You can find out what is the equivalent character for this. If you directly take a number, no problem at all. If not, as I told you, go for ASCII code. Next, plain text is equal to 6. 6 to the power of 5 mod 119. I got some ciphertext. The actual message is 6. When it is passing over a communication channel, that is the ciphertext is 41. Then the same 41 at the decryption side, that is 41 to the power of 77 mod 119. Now can you imagine 41 to the power of 77? How much time it takes? So that's why one advice to all of you is, like, when you are talking about the complexity of any algorithm, especially any operations in the RSA algorithm, there is no clear cut, crystal clear equation like you will know, right? Order of n log n, order of n square, order of log n by 2, something like that is there, no? Like that I cannot define. So well-known popular, like I tentatively I'm talking about, so approximately the overall RSA complexity will be of the order of n power 4, where n is the integer or n is the length of the encryption key. Now, how to implement this? So I think you are all aware of a small programming language. Like what I will do, as a mathematician, you might have started coding with RSA. So a small numbers, what you can do is int a comma b comma c comma d, printf, enter two numbers, right? Calculate n is equal to all these calculations. What you are doing, if they are fit into, if they are fit into your programming data types, the range of the data types, in that case no problem at all. If not, like int, long int, double, long double, they are the data types you are familiar with. Suppose if it go beyond that, how can I deal with a large prime number? In that, what we can do is we need to have an additional mathematics library. Some example, GMP arithmetic library. This I have installed on a Linux machine. Next, Sage. I have an advice for you. Sage is a library as well as it is having its own programming syntax, like your C++ or Java, whatever it is. Then one more is there, CoCal. This is also one tool to implement your cryptographic algorithm. Okay, just I will take away to some calculations. Just please give me a minute. Now I can just paste uh, I can just paste the link in the chat box. Anybody, if you are using your laptop, parallelly you can just copy paste this link in your web browser, and then you can uh, do the calculation along with me. So point number one, please have a look into that. Let's see whether I can post any message here. Yes. I hope at least some audience are using laptop. So what you can do is just copy paste this URL and just put it in the web browser. So there are two advice for you. Number one, it is you can download this Sage library and you can install into your machine, and then you can just start working with that code. But I'll not advise that in the beginning of, especially for mathematics background. So what I advise you is, now I have shared this link now. So you open that link and in a web browser, and in that web browser I will tell you small exercises, very small exercises. So I have a list of those operations, and then I will go ahead now. So this is the link. Hope you can see my web browser. I have made some some list of operations, which we can execute today. Number one, primes first in. Just what I'll do is, you can, or if you know, just type it, primes underscore first underscore n in the bracket some integer. I'll also show it to you. See, I just pasted primes underscore first underscore n in the bracket some number. What is this? It will print the first 20 prime numbers in your integer sequence. Can you have a look at this? Is it just below the here? This is the output screen. Am I right? This is the output screen. Now you want to go with a large number. Just let me see whether I can get first 200 prime numbers in your integer series. Let us see whether it is possible. Is it possible? Possible? Come on, is it possible? The last number is 1, 2, 2, 3. First,
Yes,
200.
sir.
Yes, ma'am.
Yes, sir, it is possible.
Yes. So now you can ask one thing like, sir, what is the use of it? Now, in my RSA introduction explanation, I told you, you choose one prime number in some series, some range, and another prime number in a large series. I mean, sorry, which is very uh, there is a huge difference. That should be huge difference. So what I'll do is, you can just take any one number from the tens range and another prime number somewhere in like thousands range. Calculation perspective, no issues, but it's a good practice. I mean to say, it's a good practice. So what I have done? Just to print the first n prime numbers. Next, I want the GCD of two numbers. A simple analogy. Like when you start practicing the RSA algorithm for the first time, like you will take a small number, right? So you have chosen two prime numbers, and when you are calculating the encryption key, your GCD should be there. So I'll just go back to my slide. So what is the example I have given for the value of E? It is 5. So GCD of 5 and 96, whether it is 1 or not, right? So definitely it is 1. And my suggestion is, you go with any number, any digit. Any digit means any decimal digit. See, I'll just GCD of 3 and 59. 1. So just I'll GCD of 3 and 9. 3. I will just increase the number randomly. I don't know, I have not calculated. Let the Sage Math will calculate it. So GCD of 3, 7, 6, 1, 2, 3, 9, 7, 97. Will it handle? Oh, accidentally both are relatively prime, right? So when you are calculating the encryption key, you need the GCD, and whatever may be the length of your input, you need not to worry at all. What you have to do, just put those numbers in the Sage Math library, Sage Math online tool. So we call it as online cloud in computer science language. The same link I have shared in the chat box, so you can use that. And whatever the syntax I am telling you, just few syntax I am telling you, that you can copy paste, and then or you can just type. So I will also give a link where you have a proper documentation for all the processes. So that also I am sharing you now. Probably you can just have a look into that. Right now what I am sharing is the documentation for Sage Math. First one is you are demonstrating the tool. I mean, uh, as I told you, you can just use it as a cloud platform. You need not to install anything. Second link, you can go for documentation, and then you can pick any of your applicable what is that operation, mathematical operation, and you can work upon that. Let us proceed. Any issues so far? Is it okay? Since
Yes,
it's
sir.
an
Yes.
audio.
Okay.
If any of the audience which you are, if you are already aware of it and you are expecting little more, feel free to ask. I'll do my best. Any of the audience, if you are uh, you know, you don't want to if any topics are feeling repetition, you are feel free to, absolutely feel free to ask anything. I'll help you whatever I can. Next, let us do some mod operation. Let us do some mod operation. So 23 mod 5, just click on the evaluate tree. So again, if you want to go for larger number, so that is like say for example 23,513 mod 53, just click on 34. So do you really require mod operation here? Yes. In which phase you are using mod operation? That is inverse modulo operation is there to find the decryption key, that is the value of D. Okay, so again, when you are doing the calculation for decryption key, my advice is in the beginning of your RSA journey, I suggest you to just use this tool. Or if you are okay with a normal uh, just like okay, I'm happy with the small numbers, just I want to complete my task, just I want to understand RSA working principle. In that, so many online tools are available. Just if you go to Google and then search RSA algorithm online, see, you will get so many links. See, RSA algorithm calculator online. There is some calculator from Drexel University. So many are there. Where I will take P and then I'll take give it two values, and then I'll set that. Just let us do one complete calculation. I will take P as 7 and Q as 13. As I told you, you should take little differences should be as much increase as possible. I just set. See here. Now n is equal to p into q, phi of Euler-Torsson function. Then with this available opportunities, available numbers, I should choose what? The encryption key. So if you are not believing, see, I'm just normal Google search only. I have not done anything extra. If you are not happy with this normal Google search calculator, better is Sage Math. Okay, let us proceed now. Mod we have done. Euler-Torsion function. Euler-Torsion function. Let us just click on that. Euler-Torsion function of 23. I think 23 is a prime number. Yes. So just now I mentioned that Euler-Torsion function for a prime number should be p minus 1. That is 23 minus 1. Is it 22? Yes. So you need not to worry. See, all your calculations start from a small chota examples. All your calculations start from prime only. Whatever you do till encryption and decryption, all these small examples come into picture. Euler phi function. Now, let us see some more with this library. Okay, please open the second link parallelly in your web browser. Those who are doing demonstration along with me, please open the second link in the another web tab, another tab, where we can do a lot more operations. I'm just explaining you one by one. All these things a small explanation. So you may ask one question, sir, is it possible to include everything in one file? Yes, definitely. Please follow the process. Now, I have a lengthy code I want to run all at once. I have a lengthy code. I want entire RSA algorithm to implement everything in one file. In that case, I have a suggestion for you. Please open a notepad file. Open a notepad file. In that notepad file, you copy or you type your complete program from the second link. From the second link. Okay. Like I have this. Okay. So I'll just take one more small example. See here. One array. I have taken one array. For n in the range of 1, 21, just print the relative prime number up to 20 and then append to the array. A simple program. What you have to do, you take this array, you take this program. What you have to do, copy into this empty notepad file. Okay, empty notepad file. Go to file, save as. What you have to do, you have to go and do save as. So save as, what you have to do, please make a note of the extension. Give any file name of your interest followed by .sage. .sage. S-A-G-E. So you have to store as, you have to give the name, some file name as store. File name sage. So after that, what you should do is you go to the server. You go to the execution page. You have to just give load space, load space where you have saved that file. Whether you have saved it in a desktop, whether you saved it in a D drive, E drive, or My Documents, wherever it is, you have to give that path. What is that path? Say, for example, where I have saved, I might have saved in the desktop. So you have to give that complete path. So therefore, this is one way to execute a complete program or implement more than one instruction at a time. More than one instruction at a time. Okay, fine. So now I'll go back to the demonstration in a little while, probably 6 to 7 minutes later. So I hope you got little idea how to implement RSA. Now, what are the other things we need to take care about? What are the other points? Like as a researcher or as what I can say, PhD student or even any student, what you can contribute to the RSA, I'll take up and then again I'll come back to the code. Okay. Now, security challenge. So as I told mentioned, that is your security challenge is breaking a large composite number, especially I'm worried about odd composite number, where breaking that into two prime numbers is a difficult task. Of course, all mathematicians know this, but how to making it into a uh, proper program. So for that, this is one famous book. Like if you are interested to work on prime factorization, okay, you can just make a note of this, where you can start, like whether you're a BTech student or whatever the student like even I can say PUC student also can take this. So there are some relevant information where you can do the factorization. Like see for example, Fermat's theorem. How this Fermat's theorem work? You know the basic equation of a plus b into a minus b, a square minus b square. That is a simple method which you are aware of. How it is linked with factorization? Yes, it is linked with the factorization, but the problem is, I'll just show you one example. And today we are not using this Fermat's theorem because of so many reasons. Because for some numbers, your Fermat's theorem for factorization, I'm talking, because don't get confused. There is something called as Fermat's little theorem and Fermat's theorem for factorization. So Fermat's little theorem is primality testing. Fermat's theorem for factorization, that works in a different way. So in this Fermat's theorem, what you can do is sum of the numbers, sum of the numbers, even though they are composite numbers, your program may go to infinite loop. Infinite loop. What is that infinite loop? So in that infinite loop, like you never get a plus b into a minus b. I can give you one example for that. So I mean, a long back, just imagine when there were no supercomputer, when there were no high level supercomputing power, like how they would have done, how the mathematicians they would have done. Like so, then there are two more algorithms, Pollard row and Pollard p minus 1 algorithm, where Pollard row, just I can show you one diagram for it. That is, just can you look into the uh, image? See here, all your factors are located in this fashion. All your factors located in this fashion, row, Pollard row. So my point here is, or you can put me one question here, which algorithm is better, which one we need to use, which one we need to consider for factorization, which is good. See, I'll tell you, if you are having a high level computing power, see, when I used to do this factorization algorithm in my previous CSIR lab, I used to keep the program run by, for example, before leaving the lab, 4:30 or 5 o'clock. So what happened? Next day, I used to go and check the output. But still, there were some programs which went to the infinite loop. I have a suggestion. If you want to work for prime factorization, please make a note. You should be a little aware about, parallel coding, parallel processing or parallel coding. What is that parallel coding? Parallel coding means like probably you might have aware of MPI, multi precision. Like basically you are dividing the task into different cores of your processors, get back your result, consolidate together, and print the final result. So even though there are so many algorithms which you are seeing on the screen right now, I suggest you simply randomly tell that which is better, which is not better. So as on today on paper, by looking into the history of prime factorization, I can advise you quadratic sieve algorithm is better. Okay, quadratic sieve algorithm is better. So why and all, we'll come to know that very soon. So one side, prime factorization, another side, to test whether the number is prime or not. These two are just like two lines of your railway track where uh, you keep on moving, never ending story. Even sometimes when I used to teach cryptography in my class, I used to tell it's a Tom and Jerry game. Like today, you will say, oh, ho, I have got the factors. I have got a factor of a large composite number. But tomorrow, somebody will say, no, no, buddy, just I found out one more bigger prime number than you. So, absolutely, you cannot claim that today what you have done, tomorrow it will be true. So, my suggestion is if you want to work for prime factorization, directly you can go with quadratic sieve algorithm, which is somewhat better. I can give you one new approach which I have done. Probably anybody can take up that work because I just moved to blockchain technology where I can just give that work to anyone because we have given a CSIR proposal. Well, let us see. I'll just come to that little later. Okay. Now, again, from the hacker perspective, how it should be an exponential algorithm. So when I'm using the word exponential and polynomial, on the other side, I have to use another two keywords, which is deterministic and non-deterministic. Okay. So which is polynomial? Which is exponential? What is the time complexity of all these algorithm? What is the space complexity of all these algorithm? Then what is the prime challenge or prime RSA factorization challenge happen? What is going on right now? All these things matters a lot. So I'll come to that one by one, one by one, one by one. Now, just few minutes to just think about to talk about primality testing, where you might have aware of so many methods which are very much popular in the field of primality testing. So in that Fermat's little theorem, no, I mean it's not true for all the numbers. There are some numbers which, even though they are composite, that will fail Fermat's little theorem. I can just put the name of it. It's called as Carmichael number, and that is having some special property. Carmichael numbers. That special property is just it is having three factors. Suppose you have written n as a ABC, where n minus 1 divides a minus 1, n minus 1 divides b minus 1, n minus 1 divides c minus 1. So that is nowhere linked with your RSA. Just I have why I am telling that, like there are some numbers which fails Fermat's little theorem, that is invented by a person called as Carmichael, a famous mathematician. But what is the speciality there? That number will have three factors. But are you really interested in three factors? No, in our RSA algorithm, we are not worried about three factors. Next, there are so many algorithms, Miller-Robbins law, Strassen test, all these things. But I would like to highlight the contribution by Indians, that is your AKS algorithm. So I advise you, if you are interested to work with this area, you have a methods, you have all the possibilities to improve the time complexity of AKS algorithm. Just I would like to show you that. What is that? This is called as primes in P. This is given by Dr. Manindra Agarwal ji and his team, where this is the one and only deterministic polynomial time algorithm to test whether the number is prime or not. This is called as primes in P. What is this basically about? So here we will use, I think you are aware of Pascal triangle. Pascal triangle, and a simple method. What you can do is, it is just like this. I will show an equation that is, it is just you are expanding the coefficients. You are expanding the coefficient. Say for example, given a number 3. What is that? Given a number 3. Okay, I'll just go with a little bigger number. What is that? I'll go with a 7. So x minus 1 to the power of 7. This is power, okay, minus of x to the power of 7 minus 1. Okay. What is this? This is power, x to the power. What I am doing now? I am just testing whether the number is prime or not. For that, what I need? I need to expand an equation like this. 7 is the given number. With what I am doing? X minus 1 to the power of 7 minus of x to the power of 7 minus 1. What you have to do? You just expand this equation and please check each and every coefficient of your x, starting from x to the power of 7 till 1. So what you have to do? Check all the coefficients. If all the coefficients of this expanded equation is divisible by the given number, please don't look into the sign whether it is plus or minus, just look into the number. If all the numbers are divisible by the given number, that is 7 in this case, then it is prime. If a single coefficient is not, any one I am talking about, any one coefficient is not divisible by the given number, then that is not prime. What is this? This is the one and only polynomial time algorithm. I mean deterministic, again I'm stressing on these two words: deterministic polynomial time algorithm for primality testing. So initially the complexity of this algorithm was log n to the power of 2 by 3, but there are so many improvisations happened later. Even our CSIR lab, where I was a part of that CSIR lab, we have done some work to fine tune a small delta variation, delta improvement uh, in the complexity. So why I have taken this example? Because you can take up your research in improvising this. Now, all these things, I hope. Any questions so far? Anybody? Any questions so far? Or we'll take up all at once? Okay, if all the audience are silent, I mean, I can understood like whether you are following everything or you're not following anything. Usually that's what I'll tell my students. So as a mathematician, what you can do, as a computer science background, when it comes to application side, what you can do. That is what I'm stressing now. So as a mathematician, my suggestion is don't run behind factorization. It's not advisable, because I'll show you one case study. I'll show you one link. What is the you know uh, what is the challenge, RSA challenge, which you have come across, or which is given in the long back from uh, 19, I mean, whenever 1980s, from there till today, what happened. A point to be noted is by 2020, I mean, 3 years ago, 2.5, 3 years ago, all the cryptographers, what they were telling is RSA 1024 bits will be no more. RSA 1024 bits will be no more. And we could able to successfully got the factors of 916 bits. So one professor, Dr. Veni Madhavan sir from Indian Institute of Science, a distinguished professor, and who is active member of Cryptology Research Society of India, CRSI, sir team, they were able to find the factors of 916 bits already. But really the question is, do you really need 916 bits in your day-to-day application? That is the question now. For that, I will take you to some of the real-time examples. Now, right now, I just done this Google search, right? Okay. So when you go to the web browser, in that, there is something called as connection is secure. Click on that. Certificate is valid. If you click on that, you will see some fingerprints. You can just look into this fingerprints. So what is this? So here we have SHA-256, which is well-known hash algorithm. Especially we are all crazy about this when it comes to uh, blockchain. So in this
Excuse me,
secure,
sir.
yeah,
Excuse me, sir. One
yes,
participant raised his hands. Sarang Sadavate.
just a minute, ma'am.
One of the participants raised his hands. Maybe he's
Yeah,
having some doubt.
definitely. Come on, please go ahead. Please go ahead.
Yes, yes, sir. Could you please show that secure something we shown that one, sir? Not able to
Uh,
see that
okay,
screen.
okay. Are you using a laptop?
Right now, yes, sir.
Okay. Can you just uh, see now? Are you able to see my mouse cursor?
Yes, sir.
Please click on that lock symbol.
Okay.
In that, there is something called as a connection is secure.
Okay, sir. Yeah.
Click on that,
Mm-hmm.
and you will get two options. One is certificate is valid, and one more is called as certificate is secure. You are able to see these two options. Why I
Yes,
am
sir.
showing
Yes.
this example is you can incorporate this RSA application into the real-time examples like this. Say, for example, your certificate is valid. Just click on that. See what you are seeing now. You are seeing some details, right? Even in your laptop, it might be different. So,
Yes.
yeah. So if you just click on, I mean, see all the versions, or just look into some of the hexadecimal values, what you are seeing. This is one part. Next, another part, I'll go back to the same link, same your secure. Again, there is something called as learn more. Please go to it will take you to the settings of your web browser. Here you will get some security level information. For this purpose, you can use RSA number one. Now, hope you are all very much crazy about WhatsApp end-to-end encryption. I hope you are all very much crazy about this. right? If
Yes,
I
sir.
just to show about RSA algorithm, yes, you can incorporate. Please don't look into the latest factorization research. Even I told you, Dr. Veni Madhavan sir team, they have done 916-bit factorization. But my point is, do you really need 916 bits for your application? No, never. So if you just go to your WhatsApp settings, you will definitely find this end-to-end encryption. Can I use RSA here? Absolutely yes. So what my suggestion is, as a researcher, you can take any of your day-to-day life, day-to-day real-time application, preferably if it is on the Linux platform, if they have developed on a Linux platform, you will definitely get the source code of it, find out which algorithm is incorporated there. Now, after understanding which algorithm is incorporated there, if you change any cryptographic algorithm, will it really going to be a benefit for you, or really it is going to be a burden on your computational power, computational what is it, time complexity? In all these things, you can think about RSA. Again, one best example I'll tell you. I don't know how many of you are aware of uh, some of the net banking applications. Just I will click on just login page. Don't worry, I'll not show you my password. Okay, just for, can you have a look into that? Okay, I'll just copy paste into the Word file. You can just have a look into that. Please see this. Are you able to read this? Anyone? I'll just increase the font. Still, I will increase the font.
Yes, sir. We can see.
This site is certified by VeriSign as a secure and trusted site. All information sent or received in this site is encrypted using 256-bit encryption. Just now I told RSA 916-bit factorized, but in the real-time application, how much we are using? 256. This is one application. You can go for it. Okay. Still, this is your State Bank of India. You take, you want to Google Pay, Phone Pay? Yes, I can just say security algorithm in Google Pay. Okay, you can just search on that. My advice to all of you is, please make a list of all the available day-to-day life application. In that, see where and all RSA is incorporated. If not, let us see the time complexity and all these things. And you can just incorporate and you can just come up with a protocol like this. So as a computer science engineer, what you can do, you can just write a Python program or any other programming language, how to implement this. As a mathematical person, what you can do, suppose you are aware of all these operations, right? You are already aware of so many operations in RSA. So is there any quick way or is there any possibility of improving a time complexity by a small variation? So what's happening in today's world? What happening in today's world? Like there is one more alternative to RSA which has come up. Probably that takes a complete full session to discuss upon that. So many audience here, definitely you will have a question in your mind. How many years still we have to run behind RSA? Or still, whether everyone will get a computing power, computing facility by the government of India or anywhere else? Can I implement all these things in a real time? So many questions will come to your mind. So for that, my suggestion, just understand the problem, and understand the mathematics behind that. Of course, I hope 90% of the audience will do that. Try to understand whether it is a polynomial or exponential as a developer perspective. Point number 3, how difficult, what is the complexity behind this? I forgot to add one slide in the PPT, that is discrete logarithmic problem. That is the backbone of your all your public key crypto system, whether it is Diffie-Hellman or whether it is RSA. That is discrete logarithmic problem. I think yesterday sir explained. I was also listening to that. Now, you are a pure mathematician. Yes, what you do is you can just go with, you just take this paper, that is primes in P, that is Manindra Agarwal ji. They are from IIT Kanpur. So what is my suggestion? I am just looking into that. That is, I'll just, it was not, okay, there is a question. If 906-bit RSA is breakable, also breakable, Mr. Viresh. Yeah, Viresh. Breakable means, I told you, you take one real-time example. I have sent you an WhatsApp message to you. Okay. How much time it takes to reach you? Seconds. Okay. Now, what could be the maximum length of a prime number which I am using if I incorporate the same thing, same number in any of the application? Now, 900-bit factorization is done. Okay. But if you think as just you are using it, right? Like I am a user, you are a user. We are not doing any research, we are not doing any high level coding to get the factors. Now, that's the reason I told you, when you are selecting two prime numbers, you have to uh, take two prime numbers which are very apart each other. No, that is also one of the reason where it is very difficult for an hacker to do the decryption. So now, for coming to your question, if 916-bit is breakable, yes, but even though if it is breakable, this is as a researcher perspective. Okay. So what you are telling is, I think if I am guessing your mindset, like you will encrypt using some 256-bit. We have some ciphertext. Somebody will take, and that somebody will use their supercomputing power, and they will get back my original message. That could be your reason. I'll tell you, when I was explaining about this HTTPS, what is that? Your connection is secure and all these things, right? So here, when you are trying to incorporate any of your application, day-to-day application, you are changing the cryptographic algorithm, you should take an approval from NIST. I hope you are aware of this NIST. So there they will check whether it is whether it is feasible, whether it is worth, whether it is financially worth, and all these things. So for your question, what I can say, this 916-bit factorization, what you are asking is, that is for the researcher perspective, not a real time using application. And follow the maximum, like and also please don't be in a wrong assumption telling that uh, you know uh, if you simply increase, you will get a better performance. No, it's even it is not correct. Already now, just now I have shown you the State Bank of India website, right? So if you just look into the history, this 256-bit, when it has come, probably an year ago. I'm not sure about the date. Don't be in a wrong assumption. Okay, I'll make 256 to 356. Will it be worth? Unnecessary, don't do it. That is what my suggestion. I hope you have got some clarity. So, if you are doing PhD or any research in mathematics, think about prime factorization and primality testing. Specifically, if you are targeting these two areas, now uh, there is a scope to understand, or what is that? There is a scope to improvise the time complexity of your algorithm. What is that AKS algorithm? Okay, so that you can take up as a factorization. I don't think you have to run behind RSA even after so many years, because already we have one more boss came into picture, that is called as elliptic curve cryptography. What is that elliptic curve cryptography? So just for your curiosity, I will show something, that is ECC versus RSA. ECC versus RSA. So the point is, can you just have a look into the uh, key size? Just have a look into the key size. And this is recommended by NIST, not by me, National Institute of Science, Standards and Technology. So suppose if you are having some complexity into the 1024 bits, in this case the same complexity you can achieve in elliptic curve cryptography using 160 bits. Now a common question, even it was in my mind, and definitely it was in your mind also. What is that? If this is already well settled, then why we want to go for RSA? Hmm? That is a simple question which will come in all your mind. I have an answer for this. For example, what application you are using? Say for example, you are storing some data securely. Just an simple exercise. You have Aadhaar. I think you believe Aadhaar is secure? Hopefully. Are you believing in Aadhaar? Is it secure? Can I just get one statement on it? Your Aadhaar card is secure?
We hope so.
Yeah.
We
So
hope
hope.
so.
Yes, sir.
Yes. So do you know what is the mathematics behind storing your Aadhaar securely? Anyone?
There is
It is,
one code might be. Sir.
it is your hash function. It is your
Okay.
hash function.
Hash.
That means, yeah, whenever you are storing something, hash come into picture. When you are exchanging something, encryption decryption come into picture. Before encryption decryption, you want to exchange the key, right? So my suggestion is, still RSA having scope. Don't be in a wrong assumption, because elliptical cryptography, to be honest, as a computer science background, where I did my MTech project in elliptical cryptography, I took 3 months to understand how it works. A basic equation of ellipse, and your encrypted value will be in the form of coordinate values x comma y. How to understand all these analytical geometry. So uh, what I'm telling, yes, even today both are having equal importance. You have to decide based on your application. If you can tell me what application you are building, what security application you are building, so probably I can suggest you which algorithm is better. Probably I can suggest you what all the mathematical stuff you can improvise. That is one part. The second part is, never ever tell that I am great, or never ever tell that my approach is great. So that also never works out in this field, because I have shown you so many examples, right? What is that? 256-bit encryption, WhatsApp, right? Huh? You can just go with Google Pay. Yeah, security algorithm in Google Pay. Probably they are using elliptic curve cryptography. It seems, I'm not sure. Okay, see here. Probably you just you do one thing. all the audience, what you do is you take any application in your day-to-day life, go to the settings. See, I'll go to the settings of my web browser itself. Okay. In this browser, privacy and security. Okay. In this privacy and security, what I'll do, I'll just click on the security. See here. What I am using, HTTPS or SSL certificate on your device. Click on that. See, this is the certificate. Each and every online communication will have a digital certificate. That is also an public key cryptography application. That is also public key cryptography application. Can you incorporate RSA there? Yes, you can. So, and also, can you use this prime number concept, all these exponential, all these concepts in securing your other card? Yes, you can do. If you are too much enthusiastic and too much you want to get into core mathematics, probably you come with your own approach and prove that it is polynomial or whether it is deterministic. All these things you can come up. So finally, what I can suggest is, will quantum break your RSA? Last question. Will quantum cryptography break RSA or any other cryptographic algorithm? Seriously, I did not think of it because your quantum cryptography is, or quantum mechanism is still under research, right? It is still under research. I mean, we don't have, yeah, still we don't have any solid proof. It's under experimental stage. So I have a suggestion. I want to show you some of the research labs. Finally, probably I'm on time. So please make a note of some of the research labs working on these fields. So after that, we can probably close the session. So I'll just show you some of the labs. Where and all you can apply this cryptographic algorithm, where and all you can be a part of existing. So one famous lab, happy to say that where I was a part of this lab, CSIR 4th Paradigm Institute, we have 360 teraflop supercomputer. On that computer only, I was doing prime factorization. So here, this lab, there is HPC and Cybersecurity Division of CSIR. There you can apply for your internships if you are having a solid proposal. Please follow this, number one. Number two, CDAC is doing, see, you are all aware of so many research labs, but how to approach, where to approach, how can we, write a proposal, all these things matters. My sincere advice to all of you is, when you are writing especially a security related proposal, please concentrate on number of bits, I mean key size. For example, your AES 128-bit key, right? Your DES 64 bits, and never ever think of DES, just leave it off. DES and triple DES is no more. Okay. So in symmetric key cryptography, you think about AES. In asymmetric key cryptography, you think about RSA. After that, elliptic curve cryptography. These two are enough. Don't simply think too much. Then when you want to go for storing something, again I am repeating, storing something, you go for hash. And because of that hash only, your blockchain came into exist. I think probably you are all very crazy about blockchain, right? That is also an application of public key cryptography. But we are not using RSA there. We are using elliptic curve cryptography there in your blockchain. So you just look into CDAC. You can go for any DRDO labs working on the cryptography, and what is your contribution there, what they are working, you can be a part of it. All these things you can see here. You know, CDAC is giving their supercomputing power to all the educational institute. Yes, it is. So finally, Is there any question or anything you want to ask? Please go ahead. Just I'll give 5 minutes pause. Just 5 minutes pause I will give.
Sir, good evening, sir.
Yes, please.
Sir, I have one call regarding can we relate the cryptography with the graph theory?
Yes. So in that case, cryptography with graph theory, yes, definitely, but not related to RSA. Cryptography with graph theory, yes. Uh, Hopefully, when you are talking about graph theory, are you studying some of abelian group properties and all?
No, sir, not related to
Not
groups.
related to
We are
graph
studying about
theory.
labeling.
No, according to my knowledge, I don't think graph theory. I have to find out.
Okay.
Graph theory with cryptography might be there, but I'm not aware of. I'll get back to you.
Okay, sir.
Not sure. Just we can explore. Can you please suggest masters or PhD courses in cryptography? Okay. Uh, so, Sachin, are you talking about any online course or you're talking about an educational organization to take masters or to take BTech or something?
Yeah, the proper educational,
Okay,
not
fine.
the online.
Yes. So just now I told about CSIR, right? So
Yeah,
there is something called as Academy of Scientific and Innovative Research. This is also equal to your NIT and IITs, which is of national importance. Okay, this will give you
sure.
MTech, PhD, and all ACSIR, Academy of Scientific and Innovative Research, number one, and other courses is uh, you know of course your IIT NITs all by default it will be there. So please look into this. Here we have mathematics, see, academics. Just a minute, it's loading. Okay. See, admissions, you have some, see, Vishweshwaraya PhD scheme, all these things are there. So this is one organization where you can do masters as well as uh, PhD there. So probably you should have a net score, I think so. Anyway, please look into this ACSIR. Then when it comes to academics, I'll suggest you IIT Kanpur, where they have a separate. Almost all IITs and NITs they have a cryptography lab. So courses you cannot directly take MS in cryptography. No, there will be something like MS in cybersecurity or MTech in cybersecurity. So there is nothing
Sure.
like MS in cryptography, but cryptography must be there for cybersecurity, no? Or
Right,
uh,
right.
yeah, advances in mathematics and cryptography like that. Also, some courses will be there. You can opt advances in mathematics, or simply search like advanced cryptography courses in India. You will get this ACSR. Why I have told is I was talking about CSR lab. My cryptography guru is the head of mathematics here. I mean, is all over India coordinator. So that's why I'm aware of it. Then if you go to each and every research lab, even in IISc, we have Dr. Arpita madam, and then they're working on number theory. So problem I'll tell you. Okay, the problem is what you are supposed to do, what you are planning to do. That matters a lot. Like whether you want to improve the quality or whether you want to improve the complexity of an algorithm, you have to approach which department. Like you are just using already RSA algorithm is there. You want to just use it for your computer science application. You have to go with CSE. Working on the core part of mathematical part of this algorithm. For this, what to do? You need to approach mathematics department. And one more I will suggest in Hyderabad, CR Rao. They are also working on CR Rao AIMSCS. This is one lab, complete cryptography. I think whatever cryptographic algorithms are there, they are working on it. Okay, Advanced Institute of Mathematics, Statistics, and Computer Science. Here, it's a mixture of all your protocol, mixture of all your algorithms, that, this, and all. This is one best site. You can just find out the faculty profile and you can approach. They will also take full-time PhDs. And please follow. I'll tell you 2-3 websites. Okay, 2-3 website. Of
Sure, sir.
course, you are all familiar with CRSI, Cryptology Research Society of India. Through that only, last August, I think Jinsi ma'am, she came here to our campus, through which I have got an association with your college. One other one is there, that is IACR. You can just enroll for the notification, International Association for Cryptologic Research. Take a membership of this and then just attend events. IACR. Then another advice is there is something called as IndoCrypt. I mean, I'm talking about little high level researchers. There is IndoCrypt, AsiaCrypt. So many things are there. Okay. I think, see, this time IndoCrypt is in December 17th. Every year, December, IndoCrypt will be there. So all these IndoCrypt proceedings will come in Springer LNCS. Okay. See here. So I advise you to go to this site, that is Springer link,
Sure.
where you will get lot of ideas to start your research. I'm not talking about outside India actually. I'm just talking about inside India. Yeah.
Thanks a lot, sir. Just one more thing. If I have suppose 15 plus years of experience as a software developer, so
Okay.
can I apply for PhD position directly, or I have to go the masters and PhD route?
Right now, what is your qualification?
BTech.
BTech. So I suggest you take the GATE exam. Once you qualify the GATE exam, directly you can become a JRF in ACSIR. So if you have industry experience, I'll put it in a different way. Masters is mandatory, but what I'll do is you can take your corporate and have a tie-up with some of the top-level government R&Ds and start working on cryptography. Now, may I know which domain you are working in, please?
So right now I'm in an investment bank.
Okay, not into development, anything, right? Okay.
Development. Yeah, I'm a software developer in investment bank.
Okay, like basically when when you are incorporating your security algorithm into your application, assume that you are developing a software for educational purpose. Simple example. Do you really need cryptography there? Obviously, yes, you need a cryptography there. How you are incorporating that? Because as a software engineer, you will think about what is the cost of this developing this algorithm. What is the, if I sell this product, how much I will get? I'm sure. Am I sure? Correct. So
Right.
yeah. So what is the better security algorithm you can incorporate in your product? You have to think. For that, you need to think about where and all you are deploying your code, where and all you are deploying your software. Suppose you are going with website. You are going with website. Then what I suggest is you go with HTTP. I think hypertext transfer protocol, you are all having that. If anybody is working on networking part of your algorithms, say for example, there is something called as RFC, request for comment. For RFC for HTTP, we have some documentation. In this documentation, clear cut instruction is given. Clear cut instruction I'm talking about. RFC means request for comment. All your standards will be approved by this. So you're a software engineer, You want to incorporate something, if it is related to website, go with some particular protocol, read the documentation. Definitely there will be a cryptographic algorithm, whatever they have incorporated when it started until today. All these things are available with RFC documentation. So according to that, which is the best algorithm you can improvise, that you can go for it.
Sure,
Yeah.
sir. Thanks a lot for your help.
Yeah. Yes. Anything else?
Hello, sir.
Yeah. Please go ahead.
Yes, sir. In post-quantum era, is there a threat to this RSA and all ECC?
I told you in my talk. Still, you need not to worry about quantum cryptography. It is still under research.
Sir, like IBM already developed, I think, 1024 qubit, like that. They have developed, I think, IBM.
Oh, you mean to say your factorization and all will be gone in one day? That is what your worry.
Yeah, yeah.
No, not exactly. I'll tell you one. Just now you mentioned about qubits, right?
Yes.
So I think I'm not exactly remembering something. There is one physics property of quantum. Like I'm not able to recall that. Like your quantum crypto will not suitable for all the applications what you are discussed so far from
Yeah,
class.
sir. Yes, it will be basically used for factorization and all.
Huh.
Things.
No, I mean people are fighting. People are claiming. China is claiming that 1024 is gone, no more. But I have never seen a program or I never seen a demonstration or a proper result to say that quantum is a boss now. People are talking, but I have not seen any solid proof to say that it's well in placed. You need not to worry. I think so. Okay, Viresh, you need, don't think about quantum. Just you keep on developing, keep on develop your algorithms.
Okay, sir. Okay. Okay.
Next,
Any other question? For the attention of all the participants, the feedback form link to the feedback form is given in the chat box. Please do fill that without fail. And if you have any query, please be free to ask.
Sir, could you provide us some
yes,
books,
ma'am.
reference books for the basic, for
Yes,
the
ma'am. I'll
basic
share you
knowledge?
one file, Vijay, ma'am. I'll share you one file which is completely, consists of mathematics part, computers part. I'll share you one document. You can share it with
Okay,
all.
sir. We will share that.
Yeah, probably
Okay.
I'll do a little later by
Okay.
today night.
Okay, sir.
I'm taking session by sitting in the campus only. I have to leave home.
Okay.
After
Okay,
that,
sir.
I will share. Shall I wind up, ma'am?
Thank you.
Uh, if there
Thank
is
you, sir.
Thank you very much. I will share my number and then phone email ID. Preferably, you can just contact me for any issues. I'll try to help. I have
Okay,
shared
sir.
it.
Thank you so much.
Thank you. Thank you, Vijay,
Thank you.
ma'am. See you
Thank
again.
you, sir. Thank you.
thank you, sir.
Thanks a
Jinsi.
million, sir.
Good,
Yes, sir.
good evening, one and all. It has been my honor to be part of this wonderful and informative hands on session. I'm sure that we are all blessed to attend this session by Mr. Murthy DHR on the topic Key Insights of RSA Public Key Crypto System. He introduced the RSA algorithm and well explained its complexity, introduced seed cell server, documentation of algorithms for primality test, and all. I'm sure that all participants will be benefited by this. Surely, this session motivate the growing research community. On behalf of all participants, on behalf of Department of Mathematics and Thomas College, a big Big thanks to you, sir. Thank you so much.
It's my pleasure, ma'am. It's my pleasure.
Thank you, ma'am.
Thank you, sir. The next session will start at 7:30. The link will be posted in the WhatsApp group.